we're going to finish off our chapter 5. So if you go to page 5.10, in the last lecture last week on Thursday, we talked about different devices, and the only device which is left now is what we have as nozzles. Now, you might have seen, if you're doing aerospace, then I think you are probably more familiar with the nozzles because they have a lot of applications in aerodynamics and in aerospace. Of course, when it comes to mechanical engineering and also turbines, you have a lot of nozzles as well, so that's still quite applicable. Now, you might actually have come across, if you're doing aerospace again, you might have come across that design which you've seen here, sort of a converging, diverging design, and that's one of the ways in order to have supersonic flow. We're not going to do that now in this course, but in fluid mechanics, you might come across that. Maybe you've covered it in the first semester, or maybe you'll do it next year. But let's just, for now, come back to our thermodynamic concepts and the adiabatic devices that we've been introducing. We talked about compressors, turbines, and this is one of those devices which is actually quite similar to a valve. Remember in the last lecture I talked about a valve, and I said when the flow goes across a valve, the pressure suddenly drops. When the pressure drops, temperature could actually drop as well. And this is the very useful fact about having valves or throttles. Something, first of all, about nozzles. They have very similar structure in terms of what happens. You know, you've got a change in velocity, for example. You could have that. Or essentially, you have lots of different applications. And as I mentioned about nozzles, some of the applications are in propelling nozzles. Typically, in the jet engine, towards the end, after the turbine, you've got a nozzle, and that is sort of essentially to accelerate the flow by changing the cross-sectional area. You've also got some nozzles, which are probably less known, but these small nozzles are actually responsible for, just before actually reaching the propellers in the turbines, they're actually used in order to divert the flow towards the blades. Their design is probably more subtle, compared to conventional nozzles that you might come across in different applications. But again, that's another application of nozzles. And sort of a very common type of nozzle is what we know as the convergent divergent nozzle, which you can see here. Now, the throat plays a significant role in the properties of this. Again, it's a sort of fluid mechanic problem. I'm not going to get into that because we are talking about thermodynamics here. And I want to talk about the steady flow energy equation, which is probably more important in this case. One thing, however, which I'm going to say is you have what we call the Venturi nozzle. This is another sort of common name for that combination of converging diverging nozzle. And you know that Venturi effect actually has a lot of applications in reality. Again, flow meters, control systems, lots of things actually could come and use Venturi systems and nozzles. One important difference between what we introduced last week in terms of the way that valves operate in the form of an orifice plate, and when you compare that to what we know as the nozzle, there is a very important difference between the two. That difference is that in the case of an orifice plate, you can very clearly see, because of these two sharp edges and sudden restriction of the cross-sectional area, you're going to have some stagnation around these areas, and you're going to have sudden expansion of the flow, cross-sectional area. Therefore, you're going to have recirculation, you're going to have separation. And from an aerodynamic point of view, that's not good, because whenever you have separation, you have losses. That means you are losing some of the momentum of the flow into heat through viscous forces and viscous effects. On the other hand, in the case of a Venturi nozzle, which you have here, again, a convergent diverging type of nozzle, because there's no sudden or rapid change in the cross-sectional area, then you have very nice streamlined type of geometry. and configuration, which means you're not going to have a lot of turbulence. Actually, if it's carefully designed, you're not going to have any turbulence as such. You can't see any separation, you can't see any stagnation, and therefore, what could argue that this is essentially turbulence. You're going to have turbulence created here, and because of the flow separation, as I said in the orifice plate, here you're not going to have that turbulence, which means, in this case, you're going to have some irreversible effects, which is, or losses, which in this case is in the form of turbulence, and energy really is converted from the kinetic energy into the thermal energy by viscous processes. So that's the main difference between the two, really, between the orifice plate and the Venturi nozzle. Now let's get back into the equations, the thermodynamic equations. So we're talking about an adiabatic device, right? And what we know is that in an adiabatic device, we're going to assume that the heat losses are going to be zero. So when we start with our steady flow energy equation, that's going to go very similar to the valves. We're not going to have any shaft. In this case, that's going to disappear as well. Then, if you assume that there are no losses through, for example, if you assume that there's not going to be any change in elevation, you're not going to have any potential energy either. And the two terms that you're going to be left with are going to be the enthalpy and the velocities. And of course, these are not going to be ignored in this particular case. So your balance or your equation will be reduced to enthalpy on the left-hand side, exit inlet. Again, remember that the subscript E and I. And on the right-hand side, you can have the velocity, which is going to be half v squared. In a lot of scenarios where you have this nozzle or Venturi nozzle, you're not going to actually start from, you're not going to have a proper inlet as such. You're not going to have a sort of a jet flow coming through the inlet. You could actually have what we call a reservoir, and this reservoir could be, for example, if you have this converging diverging type of nozzle, you could have this reservoir here, and this reservoir essentially would be at a certain pressure. It could be a vessel at high pressure, which is now, this shape, by the way, it looks quite weird. Essentially, just assume that this is a container, a vessel at high pressure, for example. But when you end up in that situation, naturally, you're not going to have any inlet velocity. So that term here is going to be zero in that scenario, where you have this reservoir there. In which case, the only parameter which you're really interested in finding out is the velocity at the outlet, which is this velocity exit. And in that form, and if that's the case, then you can rearrange that equation, you can get rid of VI, and then you're left with this equation, which is your exit velocity. Let's just now do one example to demonstrate exactly how you would use these equations, and you would use a nozzle where you have a reservoir essentially as a starting point. So we've got a steam, which again suggests that you have to go and use your steam table at some point. Static pressure and temperature of 100 bar and 600 Celsius, respectively, flows down a pipe at a velocity of 100 meters per second. Actually, this one is not I was wrong. Actually, this is not an example with a reservoir. It's just a conventional nozzle. So we've got pressure, temperature at the inlet. Then we've got the velocity at 100 meters per second. It is then expanded into a nozzle down to an exit condition of 6 bar and 200 Celsius. We are interested in, so this is P2 and T2. This is T1 and P1. Okay? So, and also what you know is the VI, which is 100 meters per second. Now we're going to use our equation, the simplified form of the steady flow energy equation. And by rearranging that, remember what you're after is the exit velocity. That's usually the case. You're normally after VE or V2, which is the exit velocity of the nozzle. When you rearrange the equation, it seems the only parameters which are missing from here are these two. And that is when you have to go to your steam tables and find out those values. Now, because you've got the steam and you've got the pressure and temperature, if you go to pages 7 and 8, then from here, if you find, for example, what is, you've got the superheated steam, and I'm not going to show you the details, but we're not going to have time, but you've got the temperature here, you've got the pressure here, and you've got the two conditions there. You can read off what is the enthalpy, which is in this row, for example, depending on where you are. And you can easily find the two values of enthalpy. By inserting those numbers, you get your outlet velocity or the exit velocity. Something here, this is essentially not, you don't have to do this, but it's actually a good check, because remember in the valve, in the scenario where we had the two velocities weren't the same. Remember in the last lecture I said you could have a condition, or you could have two scenarios. Let me just show you those two options. These two options here on page 5.9, I said if you do not have the same velocity before and after the valve, or in this case the nozzle, then you're going to have the stagnation enthalpy have to be equal to each other in both points. And that's exactly the same when it comes to the nozzle. So what I'm trying to do now is I'm trying to find the stagnation enthalpy for both cases and see if they actually have the same values. And if they do, which is the case here, then it shows that I've actually calculated my velocity correctly. It's a sort of a good check. Oops, sorry. It's a good check to see if you've got all your numbers correctly from the steam table, from your calculations, etc. If you've got two different figures, then you have to panic, because that just means that it's not really correct what you've done. Okay. Heat exchangers, as I mentioned, because you're going to be doing so much on heat exchangers next year in heat transfer and in thermodynamics, I'm not going to go through that, which means one or two questions in the tutorial sheets which are related to heat exchangers, you're not going to worry about those. So we're going to skip those. And I just want to, before we finish off this chapter, I want to go through this table. Table on page 5.13. This table is actually a very good summary of the devices that we've covered so far, except the heat exchanger, which, as I mentioned again, we haven't covered that. But the 1, 2, 3, 4, 5 devices that we've covered, there are some assumptions, and there are some property conserved, what you can see here. We're going to come back to this when we cover entropy, because in most cases, as you can see, entropy is the one is a property which is conserved in the case of nozzle, in the case of compressor and turbine. But it's a very good summary in terms of what we really mean, or what sort of assumptions we're making when analyzing these devices. By now, you don't know what reversible is, but the term reversible, and actually we come back to reversible when we talk about heat engines and entropy, but it's when there's no change in entropy, then you're going to have a reversible process. And of course, adiabatic is when you have no heat exchange or no heat losses, and therefore your process, you're not going to have any losses in that case. Just remember to come back to this table when we've done some entropy, and then actually a lot of these stuff would make a lot of sense. So just make a note for yourself here that we'll come back to this. Okay, so before we stop and move on to the next chapter, are there any questions? Okay, good. So let's move on to the new chapter, which is on gases. Something about this new topic is that, so in chapter 5, We did cover, for example, pure substances, and we said that if you have a pure substance, such as H2O, ammonia, or R12, etc., then you're going to be using the steam table. And I said, if you have a gas like CO2 or hydrogen or something like this, you're not going to be able to find anything in the steam tables. Who's talking? Who's chatting? I can't figure out. I think I found you there. Shh. Stop it. Just nagging my ear. Can't focus. Okay, so as I was saying, gases, you're not going to be using the steam tables. That's the only difference, really, the main thing. But again, the equations are going to be applicable to closed systems and open systems, just exactly similar to what we did for the pure substances. In fact, because you've got more applications in gases, you're going to, in a lot of situations, you're going to have a gas as opposed to a pure substance. One would argue that this is probably a more common topic, or the sort of equations that we're going to be covering here are going to be more interesting. Before I give you some background about gases, we really have to do a bit of, again, history and a bit of background information on the physics side, which I don't really like most of the time. We don't like, as engineers, we do not like the way that physicists look at problems. But we have no choice now. Sometimes they've got some good theories. So the first thing I'm going to say is that in this equation, this chapter, the main equation that we're going to be using is what we call, let's just actually put on, so I'm going to make some notes actually here. This is just a summary of the first page. It's not going to be something outside your notes. It's just a summary, which I think is actually easier if I explain on a piece of paper. In this chapter, we're going to be dealing with the equation of state. And that's the sort of equation that we're going to be using. That's the starting point for most of the equations that we're going to be dealing with. And that is essentially what we know as the PV equals RT, or PV equals MRT, depending on what view you're looking at. If it's PV RT, if this is the small v, that's the starting point. I'm going to actually come back to this, but before doing that, I want to talk about the starting point for this. We have something called the you want to actually come across that as well in chemistry and physics. We've got the Avogadro's hypothesis, which really states that, and it's actually in the first paragraph of your introduction in this, is that there's going to be equal volumes of gas at equal pressure and temperature. So if you have, let's just take one example. Let's just take, for example, CO2. If you have a certain volume, let's say you've got a container with a very fixed volume, and you've got CO2 in here. If you have the same pressure and temperature in this container, if you start counting the number of particles or molecules in this container, if you repeat this experiment again and again, so if you empty the container and refill it again with CO2, if you do it hundreds and thousands of times, still you're going to end up with exactly the same number of molecules and particles in that container. If you have the same gas and if you have the same pressure and temperature. And this was actually a very important observation because that links something important about all these gases that we have. That was the starting point. And the way that this was essentially was written was really in terms of physics. So let's just talk about physics here and how physicists actually would see this relationship, which I just explained based on Avogadro's hypothesis. So we're going to have PV, pressure, volume, equals NKT. T is temperature. N is the number of molecules. And of course, you can imagine that the number of molecules in any container, regardless of how small the vessel or the container is, it's going to be huge. We're talking about something to the power of, 10 to the power of 20, 30, etc. This is Boltzmann constant. And essentially, this is a very large number. This is, again, in the order of, actually, this is a very small number to compensate for the number of molecules. So this is going to be in the order of 10 to the power of minus 20, minus 30, etc. That is essentially the equation which in physics would describe the Avogadro's hypothesis. This is not really good from engineering point of view because it uses two very large numbers, and then if you want to do this on a daily basis and do lots of calculations for your systems, etc., this is just going to be a mess dealing with these two large and small numbers. Instead, we're going to take one more, essentially look at one more step, which is the way that chemists actually would look at this problem. Now, they are slightly closer to engineering, and the way that they look at things, as far as this problem is concerned, they introduce something very useful, and that's called the mole, M-O-L-E, and we're going to be using a lot of the definition of mole a lot actually in our analysis. So the way that chemists actually would convert this equation, and they're going to actually replace N, which is in this equation, by the number of moles, which is small n. Now, what is a mole? Essentially, 1 mole of CO2, for example, I'm just going to use CO2 as just an example. It could be H2O, it could be anything else, really whatever gas you've got in mind. 1 mole of that particular gas, CO2 for example, has exactly the same number of molecules or particles as there are in 12 gram of carbon-12. So carbon-12, something about carbon-12 is that it's actually one of the fundamental in chemistry. It's the most abundant sort of type of carbon that is available, and it actually forms the basis of a lot of calculations. And in fact, this C12 or carbon-12 actually plays an important role in terms of the definition of mole. So 1 mole of any gas is defined as the amount of that gas which has the same number of molecules as there is in 12 grams of carbon-12. That's just the definition of mole. And essentially it represents it's a volumetric representation. You might have done this in chemistry or in physics in high school, so sorry if this is all repetition, but I think we have to cover some of the basics before we go ahead and do further analysis. So as far as chemists are concerned, that equation is now converted to PV equals NA K T, and that N times Na is what we had in the original equation as the N. So that N there is now written as a number of moles times Na. And what is this Na? Na is the Avogadro's constant, which is 6.022 times 10 to the 23. And the unit is 1 per mole. So still one step easier, but still you're dealing with another very large constant. Something which is a very critical step here is the new definition, and this new definition actually is if you multiply Na by K, so you all have this very large number multiplied by the Boltzmann constant, which was a very low number, and if you actually multiply them together, multiply these two by each other, then you're going to end up with a very new or very useful type of parameter, which is the gas constant. Now, you see this very fancy way of writing R in representation in your notes, sort of a curly type of R. It's quite difficult sometimes to write that. The way I normally write it, and in a lot of maybe textbooks actually you might see that as well, it's just an R with a little vertical line just next to R, and that could represent, that's a sort of representation of what we know as the universal gas constant. This is actually quite good because this universal gas constant has a certain value, as it suggests it's universal, and it's actually 8.3145 kilojoules per kilomole Kelvin. Now, don't worry too much for now about these units. It's actually quite difficult to keep track of all these units, especially when you deal with different universal gas constant, this and that. I'm just giving you a background to this, but we're not going to really come back to this history again. We're going to be using the final equation later on anyway. But it's good for you to understand the history and the source where these come from. Now we come to engineering, and in engineering, what we are really interested is mass, because we deal with the mass of a gas or something. So it's a lot more useful to define the mass, and therefore we're going to start modifying this equation by bringing the mass and replacing the number of moles in our equation. Now, how do we do that? Well, the first thing to say is that we're going to replace n by this equation, m over capital M. Now, this bit is gets a bit confusing. Now, m, or the small m, is what we know as the molecular weight, or in some of the textbooks, sort of in more newer sort of textbooks, this is going to be called relative molecular mass. I think in the rest of this textbook I've used molecular weight because it's sort of a classical name to it, but if you come across that term, it's the same thing. And the units for that is just simply gram or kilogram, depending on what you look at. This capital M, on the other hand, is what we know as the molar mass. And it's actually the units for this is in, so that would be either in kilogram per kilomole or gram per mole, which they're exactly the same, because if you multiply both the numerator and denominator by 1,000, and you get that, just vice versa. So it's both are exactly the same. And something good about the molar mass is, and this is the important bit, the molar mass is not question dependent. And what I mean by that is that, for example, you could find tables which would give you the molar mass for example, CO2, which for CO2, for example, this is 44. You could have, for example, for O2, which is 32, etc. And this is a sort of, and I think if you look at actually your formula sheet, you find a table on the second page which gives you some of these molar masses for a sort of common gases. We'll come back to the way that these are calculated. I'm going to explain exactly how this is done. For example, carbon is 12, O2 is 32, 32 plus 12 is 44, and this is actually how it's calculated, but we'll come back to this anyway. What's the implication of introducing that equation? Going back to our PV equation, the equation of state. Now, this means that I'm going to rewrite PV equals M over capital M. I've replaced N with M over M. Then I'm going to have the universal gas constant times the temperature. And in fact, this is a new, this would lead to something new. And this is what we know as the characteristic gas constant. And the units for that is joules per gram Kelvin. Now, this R, I think this is a bit which some of you might get confused. Is this R and this R? They're different. One of them is universal, which means it's applicable to all different gases. This one, as the name suggests, is characteristic. So it's actually the value of that R is dependent on your gas, the gas that you're using. So this brings us to the very first point which I made about our equation. Because if I start dividing this both sides by m, if I start dividing both sides by m, then I'm going to have PV RT. And that's the sort of equation that we know, and we use that more than anything else. And if I divide both sides of this equation by V, then I'm going to have actually P equal to rho RT. So that was a bit of history about where we get all different forms of the equation. If you search for the equation of state, you will see any of these equations or any of these forms. And I don't want you to be confused. And if you see, for example, which one is common? For example, the PV equals nRT, for example, is actually quite common. This form which I mentioned about using the number of moles and using the universal gas constant. And once you understand where these come from, then you can convert it back into the form that you are familiar with. So that was essentially what I wanted to take away from the first page of the lecture notes. Now, if you go to the next page, again, I have a little bit of historical developments. I'm going to go through that very, very quickly. What this section would review, there are going to be 3 experiments. 1, 2, and the 3 will be on the next page, which is the Joule-Thompson experiment. You can put that as number 3. What we have, there are 3 experiments, essentially to show you that we've been saying that you've got this 2-property rule, and you could, for example, enthalpy or the internal energy could be a function of, velocity, volume and temperature, or pressure and temperature, etc. That 2-property rule that we've been discussing. What these 3 experiments have shown, these are historic experiments done in 1800s and 1600s, for example, is really that U, which is, again, remember, this is the intrinsic internal energy, and H, which is the enthalpy, they both are functions of temperature only. And I'm going to show how we find that. Now, the point of the Boyle's experiment, or the Boyle's law, really, is to show that if you multiply P by V, that would be a function of temperature. And you can see that from the equation of state as well, because you see that it's PV equals mRT. M and R essentially are constant most usually. Therefore, we can see that PV are related to temperature. And that's the point of the Boyle's law. In the Joule's experiment, which is slightly more interesting, what he did, he had 2 containers. In one of them, it was filled with an ideal gas, with the valve closed, and he had vacuum in the second container. He put the apparatus inside a water bath, and then he would monitor the temperature in this water bath. What he did then, he suddenly opened this valve and allowed the gas to go from one container to the other one and essentially expand. As soon as you do that, you can imagine that the pressure and the volume would change, right? Because the volume is now going to be doubled, for example, if that's the same volume as that. And the pressure is going to reduce because you've got more volume now. However, the temperature actually did not change. So the temperature in the water did not change, which meant that this process of changing the pressure and the volume actually didn't result in the change of the temperature. Now let's just look at the equation that we had from the first law. In this problem, we're not going to have any Q, we're not going to have any work, so these are 0, which means the change in the internal energy will be equal to 0. If that's the case, and assuming that the temperature did not change, it only results in this conclusion, that the intrinsic internal energy is a function of temperature only. It's not a function of pressure, it's not a function of volume, because if it was, and it's not a function of pressure, because if it was, then the temperature would have changed, and if the temperature had changed, U would have changed as well. So that's the point of, and that's the sort of the implication of the Joule's experiment. So what I said about U being a function of temperature, that's based on this experiment. And the third experiment, which I'm just going to look at on the next page, is actually going to show exactly the same thing for H. Let's see how that's done. This is experiment number 3. This is the Joule-Thompson experiment. In this experiment, you've got a porous plug, which is placed in a pipe. This is an insulated pipe. So flow goes from the left, and then flow comes out of the porous plug. Because this is a porous media, it has some friction, and therefore you're going to have some losses in terms of pressure. So your pressure is going to be reduced now as a result of this. Now, looking at the steady flow energy equation, which we've been covering so far and been looking at, because this is an insulated pipe, that is 0. You're not going to have any heat losses. You don't have any shaft or any work done in this problem, so that is going to be 0. If we neglect, which we can actually neglect the kinetic energy, that would be reduced, and that would be actually neglected. And because this is a horizontal problem, then you're not going to have any change in elevation. You're not on an inclined, for example, surface. Therefore, your potential energy terms will disappear as well. And what you're left with, you're going to be left with enthalpy. And therefore, you're going to have H1 equal to H2, or HE equal to HI, depending on how you define it. Again, in this experiment, there was no change in the temperature, which means the temperature before and after the porous plug, the temperatures actually were exactly the same. So delta T again was equal to 0, which meant that H can't be a function of the pressure, because pressure changed, obviously, from point 1 to 2. And it can't be a function of, for example, volume either, because volume changed as well. As a result of that, we established that H is a function of temperature alone, and it's not. So this is actually an important. It has important implications as far as the two property rules that we've been discussing so far are concerned, and that's the point of these 3 experiments there. Now, there's a part on page 6.5 which looks at the we come back to this, don't worry about this. This is just essentially what I mentioned about the dependence of H as a function of T. This bit is about dimensional analysis and looking at the PV MRT type of equation and finding out if, in terms of dimensional analysis, it makes sense. And you can follow the steps I've done here to see the dimensions for pressure, for specific velocity, volume, for temperature, etc. And then you end up with exactly a consistent dimension for R. So anyway, I'll leave that to you to go through. That's quite straightforward. What I'd like to start looking at is something important. And again, we're going to come back to CP and CV. We touched, very briefly, upon the definition of CP and CV, and I said these are quite important. These are specific heat capacities at constant pressure and constant volume. As you can imagine, in gases, these two play an important role. They play a major role because in a lot of equations for work and heat, etc., you're going to need those values. They are the ones that would relate. Let's just remind ourselves, these are the definitions, how we define them. in chapter 3, when we were talking about the first law. If you don't remember these equations, you can come back, you can go back to chapter 3 and review those. But essentially, CV was defined as essentially the ratio of du by dt, and Cp was defined as the rate of change in enthalpy based on temperature, so dH over dt. Now, because we established that U and H are only functions of temperature and nothing else, you can rewrite these equations in this form, because of the assumptions that I mentioned just previously based on those 3 experiments. So the partial derivatives really here essentially collapse, and then you have the ordinary differentiation here. Now, this bit, which we're going to expand in the next lecture, is the difference between ideal gases and perfect gases. Have you ever wondered, in lots of situations, maybe I've said ideal gases or perfect gases, and these 2 terms are actually used interchangeably. Do you know the difference? Have you thought about the difference between the 2? Some of you might have thought they mean exactly the same thing. Ideal and perfect, they're the same thing, but they're not actually. In most scenarios, the difference doesn't really make a difference, but in reality, they have a different definition. And the difference between ideal and perfect, and remember this, is in the way that we define the value of CV or Cp. If the value of Cp or Cv is a function of the temperature, then you're dealing with an ideal gas. If the value of Cp and Cv are constant, so there's, Cp is equal to this, and Cp and Cv are equal to a certain number, then you're dealing with a perfect gas, which means perfect gas is actually easier to deal with. It's easier because the value of Cp and Cv, if it's constant, is a lot easier because you can just stick it in the equation, and that's it. If it's a function of temperature in an ideal gas, then you've got one more step to go through, which means your equations will become slightly more complicated. We come back to this, I think on page 11 or 12, but let's just for now remember that this is the difference between the 2. And of course, it now makes sense. If you're a chemist or if you're a physicist and you don't necessarily deal with the thermodynamic rules and laws, the first law and the second law, then you probably don't deal with Cp and Cv. And if that's the case, you don't really care if it's an ideal or perfect gas, because they have the same properties as far as they're concerned. But when it comes to thermodynamics, then they are different. Now, we're going to start looking at the ideal gases in closed and open systems. Going back to the 2-property rule, and theoretically, I could say that U is a function, could be defined as a function of temperature and specific volume, or actually could be a function of temperature and pressure. Right? I could define U as a property based on 2-property rule. I could define them as one of these 2 combinations. If I go with the first assumption, this is how I could write my the first law in terms of du. So it's going to be du dt at constant volume dt, du dv constant temperature dv, and the right hand side would be delta q minus delta w. So the right hand side is straightforward. We've done that in the past, so it's no problem. One thing which we now know is that this will be equal to 0, because what we established was that U is only a function of temperature, and if that's the case, then that term would disappear, and this is what we know as CV, as I've just defined up here. Therefore, this equation could be written as CV dt equals delta Q minus delta W. And here's the reason as I just explained. And let's just see how that, how useful that is. Just bear in mind that this is the case where, or the sort of analysis that you're doing now, do not apply to situations where you have a change of phase. Remember, CP and CV really struggle when it comes to the phase change because of the latent heat concept which I explained. Now, if I integrate the previous equation between U1 and U2, so these are two state points, 1 and 2. The right-hand side is, again, it's nothing complicated, Q12 minus W12. And I'm going to have CV dt. That CV brackets T just defines or just explains or refers to the fact that this is an ideal gas, simply because CV is a function of temperature, and that by putting that T in the brackets in front of CV, we're just confirming that. And more generally, you could write this equation if you know, for example, at a given if you have a certain temperature, then that could be written in this form by using U0 and T0, which actually define the reference internal energy or the reference temperature. Why would we do that? Well, the reference temperature or internal energy really isn't that important, because we're not really interested in the absolute values of temperature or U. We're normally interested in the difference in delta U, delta T, etc. Therefore, it doesn't really matter what reference number you use, but that's just a way of writing this in a more generic form. And I'm just trying to decide whether we have time to go through this next bit. I was hoping to finish this off before we stop. Let me just make it. Let's just carry on for a few more minutes and see how we get on, because otherwise we're going to be running behind. So I'm going to be looking at a closed system and looking at some of the equations that we've been looking at so far. What I mean by a closed system is this. I always want you to imagine a closed system could be a piston and a cylinder, which is sealed, and you've got a fixed weight in this case. Now let's look at the equations that we've been looking at so far. So we said that CV delta T or CV dt will be equal to delta Q minus delta W. If you look at the displaced work, then that means that I could write, so let's now take delta W to the left-hand side. That's what I've done here. So just swap the two sides. And I'm going to replace delta W by PdV. PdV is the displaced work in this case where you have a moving piston. Sometimes we know that as, in this case, is equal to delta WD, which D stands for displaced work. By doing this, let's see how we can change that. Now, I could now look at the differential form of this, and I could group U and PV, and we know that that's exactly the definition of H. So I've started bringing H into my first law. And now that this allows me to replace du by CV dt, and then you could, if you want, you could retain actually dPV. Let's see what you end up with. From here to here, I've used PV equals RT. Why? Because PV, I could replace that with RT, and that's how you end up with. In what follows, what I'm going to actually, I think I'm not going to have enough time to finish this off, but I wanted to first of all, I want you to go through this analysis here. It's quite simple. It's just replacements of UPV with H. But this is going to lead to something important, and that's going to be two equations which would relate CP/CV to the characteristic gas constant, which I introduced as R. And that's actually how this is defined. It is important to know, you asked me several times, a lot of you actually, where do we have to show, in the exam, for example, or in any assignment or any exam, are we supposed to show any derivations? Well, generally, I'm not interested in derivations, and I've highlighted those derivations that are important in a lot of scenarios. But the sort of analysis that you see here, you'll find exactly the same analysis in a lot of past papers. So this part is important. Therefore, I think it's important for you to, this is important, and I want you to go through this and make sure you understand that, because you have to be able to reproduce that analysis and essentially derive these two equations.